Hello, welcome to week 6 live session of NPTEL Digital Circuits. I'm Om and today we'll be solving some questions that may help you in your assignments as well as in your exams. So in this week we will be mainly discussing about uh, flip-flops. So let us see. So we have a few types of flip-flops. So first is SR flip-flop. So what is an SR flip-flop? So what you might know is as flip-flops are small memory elements that uh, manipulate the data stored in them according to their inputs. So in SR flip-flop, what we have is when and flip-flops are since there are sequential circuits, we also have a clock. And in SR flip-flop, when S equals to 0 and R equals to 0, your next output is same as the previous output. This is called the hold condition. When S equals to 0 and R equals to 1, your next output is 0. So if you see this S and R, what does it mean? It means set and reset. When reset is 1, that means your flip-flop must reset. That means your output is going to 0. So in this case, when reset is 1, your output is 0. Similarly, in the other case, when your set is 1, your output is 0. Your output is 1. And when both set and reset are 1 together, this condition is not used in this flip-flop. This is invalid condition. So this is the truth table of the SR flip-flop. Next, if we talk about the flip-flop characteristics table. So what is a characteristics table? Same as this table, same as truth table, but here we write the next output in terms of when we also have the know the previous output, previous cycle output. So when S equals to 0, R equals to 0, and previous cycle output is 0, we know Qn plus 1. When S equals to 0, R equals to 0, Qn plus 1 is Qn, same as the previous output. So here also it is same as the previous output. In the reset case, it is always 0. In the set case, it is always 1. And when both are 1, 1, the conditions are invalid. The third thing that we have is called as an excitation table. So excitation table is almost kind of a rearrangement of this table only. When we have, we write in excitation, we write inputs in terms of the outputs. So inputs are previous input, previous output, and the current output or the next output. So 0, 0, 0, 1, 1, 0, 1, 1. So when both of these output would be same, when S is 0 or R can be either 0 or 1. In 0, 1, that means there's a shift. That means when set is 1 and R is 0, then only this condition would occur. 1, 0 case, 0. When set is 1 and reset is 1, set is 0 and reset is 1, then only this condition would occur. And when both are 1, that means reset is 0 and set can be either 0 or 1. Then with the help of this table, we write S and R in terms of Qn and Qn plus 1. Or we can write Qn plus 1 in terms of S and R. So the characteristic equation here is Qn with the help of K-map. If we write Qn plus 1 in terms of Qn, S and R, what we get is Qn plus 1 is S plus R bar Qn. JK flip-flop is another form of a flip-flop which is very similar to SR flip-flop, just that in SR, the truth table if you see for both JK and SR is almost same, just that This 1-1 condition is not invalid anymore. What happens in 1-1 condition? The flip-flop toggles. That is, the output is the complement of the previous output. Similarly, we can write the characteristics table, excitation table, and the characteristic equation is Qn plus 1 equals to J Q bar and K bar Qn. Another kind of flip-flop is D flip-flop. So D flip-flop is a very simple flip-flop. In D flip-flop, whenever uh, D, whatever is D, the same is the out uh, same as the output. So if input is 0, output is also 0. If input is 1, output is also 1 when clock is 1. So the characteristic equation for D is simply Qn plus 1 equals to whatever is the input, that is D. Another kind of flip-flop is T flip-flop. In T flip-flop, whenever T input is 1, the output is Qn bar, the opposite of the previous output. So this is the characteristic table. This is the excitation table. And if you want to write Qn plus 1, Qn plus 1, if you see from this table, it is XOR, right? Whenever both the inputs are opposite, then only Qn plus 1 is 1. So this is XOR. So Qn plus 1 is T XOR Qn. Okay, so let us take the questions first. So this is the first question. So the question is, in a JK flip-flop, toggle means what? So if we go back to the JK flip-flop, here toggle means input is 1 and 1, and output is the complement of the previous output. So the answer is change the output to the opposite state. J equals to 1, K equals to 1, Qn plus 1 equals to Qn bar. This is the toggle state. So next question is, what is the output of SR flip-flop when S equals to 1, R equals to 0? So if you remember SR flip-flop, I just write the truth table again. This is the SR flip-flop when S equals to 1 and R equals to 0. When S equals to 1, R equals to 0, output is 1, set as 1. So that's A. Third question is, the waveform indicates the operation of. So we have been given this input waveform and this output waveform and this clock. We have to tell what which of these four options correspond to this in clock input and output state. So the first thing to solve this question is you analyze your when is your output changing, right? So if you see whenever you the output is changing whenever you have a rising clock, right? Only on these edges your output is changing. That means this is a positive edge triggered flip-flop. So whenever the clock edge is positive, there will be some change. So all of the options were positive edge only. Now we have to figure out what does this input output combination correspond to. So if you see, we will write the input and output at all positive edge stages. When input is 0, output is 0, input is 1, output is 1, input is 0, output change to 0, input is 1, output change to 1, input is 0, output change to 0, input is 1, input is 0, output is still 0, input is 1, output change to 1. So if you see in all the positive edges of the click clock, input is equals to output, and this is a characteristic of, if you remember, D flip flop. In D flip flop, the output is same as input. So this timing diagram is for a positive edge trigger D flip flop. In D flip flop, positive edge triggered where Qn plus 1 equals to D. Okay, let us go to the next question then. The flip flop converted from JK flip flop is. So in front of JK flip flop, we have attached some combinational circuitry. Now we have to tell which flip flop this corresponds to. So I will write the truth table of JK flip flop just to help solve this question. Now what do we have to do? We have to see an X and Y change. What is the condition of J and K and what is the output? Then only we can draw some parallel between X and Y and Q and write some output. Let us take all the cases 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so let us tackle this. When X is 0 and when Y is 0, so these two are AND gates. Whenever they have 0 here, output will always be 0. So J and K are also 0. And in 0, 0 case in JK flip flop, we were Qn, previous output. Qn, we call this. Next state is when X is 0 and Y is 1. So let us make some changes here. When X is 0 and when Y is 1. Here it is 1. Here it is 0. So in a NAND, if you know NAND gate, whenever one of the inputs is 0, output is always 1 in NAND gate. So here the input to this NAND gate is 0 and 1, so output is 1 here. So if it is 1 here, this AND gate output is no matter what 0. This AND gate output is 1. So this condition is 0, 1. And then 0, 1 condition in JK flip-flop is 0. Then the next condition is 1, 0. X is 1, Y is 0. So here it will be 0. It is again 0, 1. 1 will be here and it will be 1. It is a 1, 0 condition. And in 1, 0, your output is 1. Last condition is 1, 1. So let us take 1, 1. It is 1, 1. Whenever it is 1, 1, the NAND gate output is 0. So here it is 0. So if these are 0, these will also be 0. So JK condition is again 0, 0. 0, 0. It is again Q1. That means it does nothing. So now what kind of flip-flop this is? So if you remember the SR flip-flop table, so this is same as this X, Y, and Qn plus 1 is same as SR flip-flop. Just that 1, 1, nothing happens. Same here, 1, 1, nothing happens, and is an invalid case, which usually do not give. So here S equals to X equals to S and Y equals to R. So the answer is this flip-flop converted from JK flip-flop is in SR flip-flop where X equals to S and Y equals to R. So next question is, which of the following is correct for D flip-flop? So if you remember the D flip-flop, and what happens in a D flip-flop? Whenever so whatever is D, that is the output. So the output is either set or reset as soon as D input goes high or low. So this option is correct. What are the other options? The output complements follows the input when enabled, which is false. There is no complementation here. Only one of the inputs can be high at a time. There is only one input. The output toggles if one of the input is held high, which is also false. There is no toggling here. Okay, the next question is implement D and T flip-flop using JK flip-flop. So how to do this? Let us first do D flip-flop using JK flip-flop. So there are a few steps to it. Step one is for any flip-flop conversion, what we do is write characteristics table of D flip-flop. That is which flip-flop you want to make. Step two is write excitation table of JK flip-flop. That is the flip-flop with which you want to make the D flip-flop. And third is write J and K in terms of D and Qn. So let us see what does this mean. We first write the characteristic table of D flip-flop. So if you remember the characteristics table, this table is input and previous output give you next output. So when it is 0 0 0 1 1 0 1 1, and in D flip-flop, whatever is the input, that is the output, right? So it will be 0 0 1 1. Now if we want to write the excitation table, say excitation table of JK. So in excitation table we have Qn plus 1, J and K. So whenever this is 0 0 0 1 1 0 1 1. So when this is when output and input are same 0 0, it is 0 cross is 1 1, it is also 0 cross here, it is 1 cross cross. So this is the excitation table of JK flip-flop. Now the third step says write JK in terms of D and Qn plus 1. So what we will do, we'll take these inputs and write JK here. So when both are 0, 0, this is 0 cross. When it is 1, 0, it is cross 1. This is 1 cross, and this is cross 0. Now what you can do is, now to write JK in terms of D and Qn. To write JK in terms of D and Qn, you can make K map, right? You make two K maps, one for D and one for Qn, one for J and one for K. So for J, so J is 1 when D is 1 and Qn is 0, and D is 1 and Qn is 0. This is 1. Then this is cross, and 0, 1 is also cross, right? In K flip-flop, this 0, 1 condition is 1, 0, 0 is cross, 1, 0 is also cross. This is 1, and these two are cross. Now, if you want to make pairs, this is one pair in this one, this is one pair in this one. So we can write J equals to D, right? And K equals to D bar. So what we got is J equals to D and K equals to D bar. Now to make JK flip-flop, to make D flip-flop or to JK flip-flop, what we have to do? So we have J equals to D and K equals to D bar. Now this is your D flip-flop, which is made from a JK flip-flop. So we have implemented D. Similar thing we have to do for T flip-flop also using JK flip-flop. So for T flip-flop again, first we will write characteristic table of T flip-flop and excitation table of JK flip-flop. So characteristic table will be TQN QN plus 1, 0 0 0 1 1 0 1 1. So if you remember, in T flip-flop, whenever input is 0, output remains same as QN. Whenever input is 1, output changes its shape, flips. The citation table of JK we just wrote. It's Qn plus 1 JK 0 1 1 0 1 1. It is 0 cross 1 cross cross. Now next step is write this JK here in form of this Qn plus 1. 0 0 is 0 cross, 1 1 is cross 0, 0 1 is 1 cross, 1 0 is cross 1. Now Again, we need to make two K maps, one for J in terms of T and Qn, and the other one is K in terms of T and Qn. So for J, we have J is 1 when T is 1 and 0, and it is cross and cross, and it is 0, 1 and 1, 1. So 1 and 0 is 1, and 0, 1 it is cross, and 1, 1 it is cross. Okay, it is 1 when it is 1, 1, and cross in 1, 0 and 0, 0. Now we can make the groups. This is one group, this is one group. So J equals to T, also K equals to T. So your flip-flop will be both are equal to T. This is your T flip-flop in terms of JK flip-flop. So the answer is option B. J equals to D, K equals to D bar for D flip-flop, and J and K equal to T for T flip-flop. So what are the steps for conversion of any flip-flop into another flip-flop? First, write the characteristic table of flip-flop that you want, excitation flip-flop of the flip-flop that you have, and then write the outputs in terms of the previous flip-flop, make K-map and find the result. So next, look at the next question then. The truth table of an XY flip-flop is shown below. Design the flip-flop using GK flip-flop. So we have to make XY flip-flop using GK flip-flop. So for this, again, at first characteristic table for XY, second excitation table for JK, third write JK in terms of XY and Qn. The third step. So first let us write the characteristic table for XY flip-flop. So we will write this characteristic table with the help of this truth table. So let me just copy this truth table there. Let's write it. Okay. So when input is 0 0, output is qn bar. Input is 0 0, output is qn bar. Input is 0 1, output is 1. 0 1, output is 1. Input is 1 0, output is 0. Input is 1 1, output is again qn bar. We have written the characteristic table. I will remove this truth table for now. Second thing we need is excitation table for JK. The excitation table. Now we will write JK here. When it is 0 1, it is 1 cross. 1 0, it is cross 1. In 0 1, it is 1 cross. 1 1, it is cross 0. 0 0, it is 0 cross. 1 0, it is cross 1. 0 1, it is 1 cross. And 1 0, it is cross 1. So we have written J and K in terms of Qn and Q bar using this table. Now third step is we have to write J in terms of X, Y, and Qn, also K in terms of X, Y, and Qn. So we need two K maps. We will have three input K maps now. We write it like this. We'll copy this for K also. Now if we fill this, X is 0, Y is 0, Q is 0, J is 1. So 1, then it is cross, then it is 1 here, cross, 0 here, it is cross, 1 and cross. This for K, it is cross, 1, cross, this is 0, cross, 1, cross, this is 1. So let's make pairs now. This is one pair and one quad, this is another quad. And here also, this is one quad and this is another quad. So we can write J equals to X bar plus Y and K we can write as X plus Y bar. So we have J equals to x bar plus y, k equals to x plus y bar. So if we want to make the flip-flop, we have x and y, or gates here, x bar and y, x and y bar. So this is your XY flip-flop in terms of GK flip-flop, right? So we learned a few things here. First is this XY flip-flop is not something that we know already. So with the truth table, we easily formed the characteristic table for XY, and then we did the flip-flop conversion using the same three steps which we have used previously. First, we write the characteristic table for XY, which is this. Then we write the excitation table for XY, excitation table for JK flip-flop, and then we write J and K here. And then write JK in terms of XY and QN. And then we have our XY flip-flop made from JK flip-flop. So our answer is D option, J equals to X bar plus Y and K equals to X plus Y bar. Now let us look at the next question. Please read this question first. Okay, so let us see here. We have Given the sequential circuit is designed using JK flip-flops, is initialized with Q2, Q1, Q0 equals to 0, 0, 0, 1, 0, 0, and the state sequence for this circuit for the next six clock cycle we have to tell. So if this is the initial state of the outputs, we want to write what are the next three states of the output for the sequential circuit. So this is J2, J second J flip flop, JK flip flop, first J flip flop, zero JK flip flop. So, so if you see Q2, Q1, 0, this is MSB, LSB. Okay, so let's first write the connections. So J2 equals to Q1 bar, K2 equals to Q0, J1 equals to Q2, K1 equals to Q2 bar, J0 equals to Q1, K0 equals to Q0 bar. These are the conditions. Now I'll just copy these here, the next page. Okay, we will write the truth table of the JK flip-flop. Okay, so we have here, say this is the cycle, this is Q2, Q1, Q0, then we have J2, K2, J1, K1, J0, K0, and here Q2 plus, Q1 plus, and Q0 plus. Make some space. Okay, so this is our cycle, this is our, say, present state. These are our inputs. This is the next state. So in the question you are given, initially we have 1, 0, 0. So in the initial we have 1, 0, 0. Now we have to write what are the next output for cycle 1, 2, and 3. Okay, so when we have 1, 0, 0, our J2, K2 will be Q1 bar, K2 will be Q0, J1 will be Q2, K1 will be Q2 bar, J0 will be Q1, and K0 will be Q0 bar. Okay, now with these conditions, when J2, K2 is 1 and 0, your Q2 plus will be, when J2, K2 is 1 and 0, Q2 plus will be 1. This is 1. When J1, K1 is 1, 0, it will again be 1. When J0, K0 will be 0, 1, it will be 0. So our next state is 1, 1, 0. So I will write 1, 1, 0 here. When we have 1, 1 and 0 is the present state, then we have to write these combinations again with the help of these. So when J2 is Q1 bar, Q1 bar is 0, K2 is Q0, Q0 is 0, J1 is Q2, K1 is Q2 bar, and J0 is Q1, K0 is Q0 bar. So now again we have 0, 0, 0, 0. The output is same as previous one, which is 1 here. In 1, 0 case, it is output is 1, and 1, 1 case output is toggle, so it will be 1. So this is our next state, 1, 1, 1. We'll again need to write this all the J's in terms of previous ones. This will be 0, this will be 1, this will be 1, be 0, it will be 1, this will be 0. So with the help of these equations, we know these, we have written these. Now next thing is again writing next outputs. In 0, 1, and this will be 0. In 1, 0, this will be 1. Again in 1, 0, this will be 1. So next output is 0, 1, 1. So these are the next three outputs. This was our initial output. These are the next three outputs. So the cycle is something like this. Started with 1, 0, 0, then it went to 1, 1, 0, 1, 1, 1, then 0, 1, 1. So answer is 0, 1, 1, 1, 0, 1, 1, 1, 0 is 1, 1. Option B. So let us see the next question now. What will be the output signal frequency if 4 T flip-flops are connected in cascade? Given the input frequency of the T flip-flop is 400 Hz. So, this is a very simple question. So, in T flip-flop, when connected in cascade, what does this mean? So this is the cascade connection. And you have some clock here, which is of 400 kilohertz, and your input to the T is the complement of the output, so it toggles again and again. And the same T is sent as clock to next one. This T is sent as clock to next one. And this T is sent as clock to next one. This is the cascade connection of T flip-flops. And what happens at each stage? At each stage, frequency is divided by 2. So if here it is 400 kilohertz, here it will be 200 kilohertz, it will be 100 here, 50 here, will be 25 here. So your output frequency equals to input frequency divided by 2 to the power number of flip-flop, which is 400 divided by 2 to the power 4, which is 400 by 16, which is 25 hertz. It was not kilohertz, I apologize, it was hertz. So the answer is option B, 25 hertz. You just need to remember this. In cascade connection. This is only true for cascade connection. Okay, let's see the next one then. The following synchronous sequential circuit is designed with a JK flip-flop and a T flip-flop with JA equals to A plus B bar, KE equals to A bar plus B, TB equals to A. If the initial state of AB is 0, 0, find the sequence of states listed by the circuits. So you have to tell the next 3 sequence of states. So what I will do is first write the given information. What we know, initial state of AB is 0, 0, and we have J, K, and T equals to, let's write as a J, K, and T. J is A plus B bar, K is A bar plus B, and T is TA. T is A. T is A. Now we will write the characteristic equation of JK and characteristic equation of T. For T, it is T Qn bar plus T bar Qn for This P XOR Qn. For JK, it is Qn plus 1 equals to JQn bar plus K bar Qn. Now what we can do is we can write these outputs. So, actually if you see here Q equals to A, right? And here Q equals to B. So we can write here An plus 1, which is same as Qn plus 1 for this flip-flop. An plus 1 is JQn bar plus K bar Qn. And here for this one, Bn plus 1 equals to T XOR Qn. Right? This is here Q equals to B. So this Qn plus 1 is Bn plus 1. Now I'll write the values of J, K, and T from here. So this will become A plus B bar Qn bar plus A bar plus B Qn equals to, and we'll replace this Qn again with A plus B bar to A plus A bar plus B whole bar B Qn is A. We know here, and Qn equals to B, we know here. Okay. So this is A bar plus A bar B bar plus A bar. Okay, this we need to solve as expand plus. It will be by applying De Morgan's. In this, we will get A dot B bar A. This is 0 plus A bar B plus A B bar. A bar B bar, yeah, A bar B bar. This is B bar. A plus A bar will come common, so this is B bar. An plus 1 equals to B bar. Same thing we do for here. T is A, Qn is B. It is A XOR B. So what we have is An plus 1 equals to Bn bar, and Bn plus 1 equals to T An XOR with Bn, right? From here, what we can do is write the present state and the next state. We have 0, 0 is the present state which was given us here. Then we will write the next states. An plus 1 is Bn bar. Bn plus 1 is An XOR Bn, which is 0. Then this 1 0 will become the present state. En plus 1 is Bn bar again. This is XOR. So 1 1. Bn bar is 0. This is 0 0 0. Then this 0 0 will again become 1 0. And this cycle will repeat 1 0 1 1 0 0. It will be like 0 0, then 1 0, then 1 1, and this repeats. So our output will be 0 0 1 0 1 1 and 0 0. It is option B. So look at it again. We are given what is J, K, and T in terms of A and B. We wrote that. Then we wrote the characteristic equation. What is actually this Q in terms of J and K, and what is this B in terms of T. We wrote that. Then we replace Q with A. Q here Q with B. We found out An plus 1 equals to Bn bar, and Bn plus 1 equal to An bar XOR Bn. An XOR Bn. Then we could simply write the present state and next state with help of these two equations. 0 0 equals 1 0 1 0 1 1 1 0 0, and the cycle repeats. See the next question then. Consider the following sequential circuit to determine the state sequences of Q0 Q1 for next 4 clock cycles. Initial state is 1 1. Okay, so we have T flip-flops. So right, clock T0 Q0 T1 Q1. So here if you see, one thing interesting is this, let me call it T0 Q0 T1 Q1. Here the Q0 serves as clock to T1. So when Q0 changes from 0 to 1, this is the positive edge, then T1 flip-flop will trigger at the positive edge. So the initial case we are given Q0 is 1 and Q1 is 1. Next we have to write what is the next state. So both T0 and T1 are always 1. Because of the connection here. This is 1. So that means there will be always toggle. So Q0 will always toggle in every cycle. So clock is directly here. So at every clock cycle, Q0 will toggle, right? As in T flip-flop, whenever positive clock cycle will occur, if T equals to 0, output remains as Q1. If T equals to 1, it Qn bar. So it will always go to Qn bar. Here, like the positive edge, then it is positive edge, then it is positive edge, positive edge. So it will be 1 0 1 0 1. It is always flipping, right? Now for this T1, we know this Q0 is the clock, right? This Q0 is the clock, and this will only trigger at the positive edge changes of Q0. When Q0 goes from 0 to 1, your T1 flip-flop will trigger. So this is a negative edge, 1 to 0. This is a positive edge. Right? So here it will trigger, it will remain 1, it will go 0 here. Again a negative edge, it is going from 1 to 0. So it will remain as 0. Here it is going from again 0 to 1. So it will trigger from 1 to 0. So it will trigger from 0 to 1. So your next states are, you started with this 1 1, next is 0 1, then 1 0, 0 0, then again 1 1. You have 1 1, 0 1, 1 0, 0 0, then again 1 1. So this output is, what are the next four states? 0 1, 1 0, 0 0, 1 1. Option A. So the only thing here to take care of is, we know T flip-flop, we know its truth table. This is very simple. Whenever the T is 1, it will flip. Whenever there is positive edge, there is a positive edge triggered. So whenever there is positive edge on clock, but here clock is not same in both. Here we have an initial clock, but here this Q0 output serves as clock to this one. So whenever this Q0 flips from 0 to 1, its positive edge will serve as a trigger for this flip-flop. That is what we had done there. For first, we have the clock. For second one, this Q0 is the clock. Next question is, implement T flip-flop using D flip-flop. So we have done many conversions now. So what are the steps? Right? Characteristic equation, characteristic table of T flip-flop, excitations table of D flip-flop. Third is, right, D in terms of Q1 and T. So start this. What is the characteristic table of T flip-flop? In characteristic table, what we have? T, Qn, Qn plus 1, So whenever t is 0, output remains same. It is t whenever t is 1, output flips. Excitation table of whatever is this output, d is same. Now we write this d here, same as qn plus 1. Now next step is we write d in terms of t and qn. 0 0 it is 0, 0 1 it is 1, 1 0 it is 1, 1 1 it is 0. So with these two spots, so d equals to t bar q plus t q bar qn bar, which is t XOR qn. So we have d equals to t XOR qn. So we have a t flip-flop. So this is your t flip-flop from d flip-flop. So the last question for today is, in the circuit shown, choose the correct timing diagram of the output Y from the given waveforms W1, W2, W3 and W4. So we have to tell what will be the waveform or output Y among these four possible choices. So solve this. First copy this timing diagram. Copy the second part also. Try to match these lines. Okay. This. Okay, so what is actually y? It is called as q1. Let us call this q1 is q2, y equals to q1 and q2. So both are D flip-flops, so and both are negative edge trigger, right? Whenever there is negative edge on the clock, there will be change in output. Let us make waveforms for q1 and q2 first. So q1 the same as x, q2 will be same as y. Output will be same as y whenever there is clock trigger. So start with 0 at this negative edge. Input still 0. It will remain 0 then. At this negative edge, input has changed to 1, so this output will become 1. This negative edge, input is still 1, remain 1. Here also it is still 1, so it will remain 1. So I will write it again with some different color. Okay, so next is Q2. Q2, sorry, this is not Y, this is so now Q2 will be same as X2 whenever there is clock trigger. So we start with 0. When this clock triggered here, it is 0. Right? You see there is little shift. So it will remain 0. At this trigger also, this is 0 here. So it will remain 0 again till next trigger. Here also it is 0, so it will remain 0. Here it is 1, so it will go to 1. And your y is what? Q1, Q2. So y will be, when both are 1, it will be 1. Right? It will be 0, 0 here. It is 1 and 0, so it will remain 0. It is 1, 1, then it will go 1. So this is your y. Change in the last negative cycle. So this is same as W3. So the answer is W3. So W3 is the current representation of Y. So just two things to remember here. One is take care that this is negative edge. Since there is a bubble here, if you see there is a bubble, that means here negative edge triggered. Negative edge triggered means at the negative edges of clock, when clock goes from 1 to 0, then only any change would happen, and that change would be same as whatever is in input, because this is a D flip flop, right? These are D flip flops. So we get W3 as Y. Okay, so that is all for today. If you have any questions, please you can email me. And the next week also we will meet at the same time. Not our usual time. Our usual time is Tuesday at 6 p.m. But we will meet on Saturday. for these 2 weeks as I have some work on Tuesday. Okay. So thank you all for joining. See you next week. I'll upload the recording as well as these slides in the Google Sheet that you shared with you. Thank you.